This is MATHguide.com, and my name is Mark Karadimos. In this lesson, you're going to take a look at how to take a fraction, a rational expression that is, and break it up into separate rational expressions. So you're going to see two examples, one of which will have repeating linear factors. Okay, let's get started. As you can see, we've got the first example up there on the screen, and I'd like to tell you about all the different steps that you have to take in order to work this partial fractions problem. So the first thing we're going to have to do is set up some fractions. In other words, break this down into a sum of smaller fractions. The second step is we're going to get a common denominator. We're then going to find an equation to work this problem. And then we're going to solve that equation and then finally write the solution. All right, well, let's start. So for this problem, we really, in order to get a feel for this problem, really dig in, is we're going to have to factor the denominator. So the numerator is fine just the way it is. I'm going to attack this denominator. And I'm going to factor this as x times x is x squared. And we know, of course, that minus 5 and plus 4, they multiply to negative 20 and add up to be negative 1. So that factors there. Now, when we start the first step, which is to break this down into a series of smaller fractions, what I mean by that is we have these linear factors here in the denominator, and when we separate this into a sum of, got to work on my horizontal lines there, but when we look at a sum of two rational expressions, otherwise known as fractions, I'm going to take each of those factors and create a different rational expression, and I'm going to find the sum of those. You'll notice that this denominator is degree 1. I know you don't see it there, but there really is a 1. In other words, that's a degree 1. The numerator is always going to be 1 degree less. So if this is degree 1, I know the numerator is just a constant. It's got to be degree 0. So I'm going to represent that constant with the letter A. Now this numerator, I'm going to have to write with a numerator that is of 1 less degree than the bottom. Again, the bottom has a degree, yikes, it has a degree of 1, and 1 less than that would be 0. So in here in the numerator, there we go, that's degree 0. There's no x term. I'm using two different letters because I'm going to assume that these two numerators have different values. They could have the same value, and that'll all come out in the mathematics if that's true. But I'm going to assume that they're different variables because they're going to be different constants. All right, well, the first thing you're going to want to do is get a common denominator. So when I'm looking at the denominator, I'm noticing that this denominator is missing a factor of x plus 4. So what I need to do is I need to multiply the top and bottom of this rational expression by x plus 4. This one over here is missing a factor of x minus 5. So I need to multiply the top and bottom by x minus 5. Okay, so I'll do that. And when I do that, I'm going to get this. I mean, the left isn't changing, so I'm not even going to bother doing anything here with the left side. So the left side's still the same. But over here in the numerator, I'm getting a x plus 4. And over here, I'm getting b x minus 5. There we go. Okay, and of course I'm getting the common denominator right here, x minus 5, x plus 4, x minus 5, x plus 4. All right, now in order to add these two, I needed that common denominator, which I now have. When I add those two, I'm really going to be adding the numerators. And I'm going to get this. And if I multiply through, I'm going to get ax plus 4a Yikes. Okay, haven't made a video in a while, so I'm a little choppy here. So I'm going to get b times x, bx, 5 times, or negative 5 times b is negative 5b. And I'm going to have this all over the common denominator. Maybe I should write it. Okay, so here's my common denominator. And over here I get the same thing, right? This didn't change at all. X minus 5, x plus 4. Now the only way that these two rational expressions can be equal to each other is they have to have the same value. And if the denominator here has the same denominator here, and these two rational expressions are equal, then it stands to reason that the two numerators have to be equal, right? The denominators are equal, two fractions, the numerators have to be equal. If the numerators have to be equal, then here's where the interesting part comes in. I now know that this x term here, this 10x, has to be the sum of these x terms here also, right? I know that the ax and the bx, when I find their sum, it's got to be equal to 10x. Okay, so that means the a plus b has got to be 10, right? So the x terms here have to be the same as the x terms here, mathematically speaking. So what I do now is I start setting up some equations. Okay, so I'm now going to say a plus b is equal to 10. I also know that this negative 23 is the constant. Well, the 4a minus 5b, there's the constants over here. So the sum of these constants has to be equal to this constant, which is negative 23. All right, so that means 4a plus minus 5b has got to be equal to negative 23. Okay. Now it turns out that there's many ways to solve this system. You could use matrix equations. You could use reduced row echelon form. You could use the elimination method. You could use any method you wanted to use. Well, I'm going to solve this system of equation not by elimination, not by matrix equations, although I could do those. I'm going to use reduced row echelon form. Yes, it's kind of fun to use the calculator, so I'm going to pull that up. So here I've got a TI Inspire calculator waiting. I'm going to pull up calculator. And if you hit the button right by the 9, you're going to see this, what looks like a 3 by 3. So I'm going to click on that. I am now going to use, let's see, 2 rows. So let's see, 2 rows, 3 columns. Yep. And I'm going to put my numbers in there. So I wrote this down. So it should be 1a plus 1b equals 10. And then we put a 4a minus 5b equals negative 23. All right, so you punch this in and you get this matrix. Now you go to matrix, vectors. We want not the row echelon form, we want the reduced row echelon form, our REF. It's saying, hey, what do you want to do? Our REF of what? That. So you use your up arrow, press enter, and plow. There it goes. Press enter again, and it gives us our answer. Right here in the last column, the first column was A's, so your answer is, for A, is your first number, 3. Since your second column was B, then the second number is B. There you go. Okay, so we got 3 and 7. Let's remember that. Okay, so I'm going to go back over here, and now I know that A was 3, correct? Yep. And the B was 7. So what you're going to do is now write that as an answer. So I'm going to try to put this in a different color. Since we found A to be 3, B to be 7, I'm now going to write that as an answer. So I'd say, here's the original problem, and I'm now going to write the answer. So A is 3 over x minus 5, and B is 7 over x plus 4. So you always want to write the original problem and the answer together because it's the combined problem answer that goes together. Great. We're going to go on to the next example. All right, here comes example 2. A little bit harder, as you can see. It looks a little bit nastier, a lot of larger coefficients. First things first, let's factor that denominator. Most of the time the denominator will be factored for you, but sometimes you got to factor it on your own. And it's a nice little exercise in factoring anyway. Well, it's partially factored already, so we already have an x out there. And it turns out that this isn't really that hard to do. It's just x minus 3 times x minus 3. And instead, I'm just going to write that as x minus 3 squared. Two factors that are the same. So we say that this has a repeating linear factor. See that x minus 3, that's linear, and it's repeating. See, you got a 2. There's more than 1. It repeats. Okay, so how do you deal with this? And this one's a little bit different, so you're going to have to be a little cautious when you go to the setup. All right, so when you set the denominators up, as you expand this into smaller size rational expressions, you're going to have to first take, well, one factor is x. The next factor is one of these x minus 3s. And the second factor, the third factor, if I could count, would be the x minus 3 squared. Yep, it's a little strange, right? You say, well, I already have the x minus 3. Why do I need an x minus 3 and an x minus 3 quantity squared? Well, if I just left just the x minus 3 squared, you're leaving out the possibility there could also be an x minus 3. If you leave out the x minus 3 squared, you're leaving out the possibility that there could be an x minus 3 squared, right? That's why you have to include both. Yeah, lame excuse? This is how it works. If this was x minus 3 quantity to the 5th, horrible problem, you'd have x minus 3, x minus 3 quantity squared, x minus 3 quantity cubed, x minus 3 quantity to the 4th, and x minus 3 quantity to the 5th. Horrible problem, mind you. But that's how the problem would look. You'd scale them up. So basically, whatever that power is, you'll have all the powers underneath it. X minus 3 squared, x minus 3, all of them. Okay, well, that being said, now let's figure out how do you find expressions for the numerators. Okay, so here this is degree 1, so I'm going to use 1 degree less in the numerator. This is degree 1, I'm going to use 1 degree less in the numerator. And a lot of people wrongly think that this is going to be second degree, right? Because if you multiplied this, you'd get a square. And you think, oh, that's degree 2, so the numerator should be 1 less, degree 1. So you think, oh, this is going to be a cx plus d to have 1 degree less, some polynomial of degree 1. Nope. You just take what's inside, and what's inside is an x minus 3, which is linear. So I'm going to use a c there, okay, which is degree 0, 1 less. I know that's a little strange, but when you have these repeated factors, you don't look at the outside to determine the degree. You look at the inside. Okay. Whew! All right, now let's move on. Let's figure out how to get a common denominator. That's the next step. So you could see that this denominator is missing the x minus 3 quantity squared. So I'm going to have to multiply x minus 3 quantity squared, top and bottom. This one's just missing, well, let's see, it's missing a factor of the x, and it's missing a factor of x minus 3. Okay, what is this denominator missing? It looks like it's missing a factor of the x. Now, if any of this hasn't made sense in this video, I'm going to put links in the bottom of this video. Somewhere you could see it down there. And I'll have some other links to MATHguide, which shows you how to add. Maybe you need to back up and watch another video about how do you add rational expressions for this to make sense to you. Maybe you need to practice that before you move on to what we're doing now, which is partial fractions, something more advanced. Yeah, by the way, this allows you to do problems in calculus, which you're going to have to integrate strange things. All right, that being said, let's now multiply through. So this is going to be a times the quantity, x minus 3 squared. This is going to be b times x minus 3. And over here I'm going to have cx. Now if you remember the other problem, we could see that we've created the common denominator. So I'm going to be adding all of these numerators, and they're going to be sitting all over the common denominator. That's the common denominator right there. So really what happens is, when I take the sums of these numerators, it's got to be equal to this numerator. Okay, sorry, a little wobbly there, but I basically took the numerators here and the numerator there, and the sum of these numerators equals that. Okay, so let's now multiply all this stuff out. So this is x minus 3 quantity squared. That's x squared minus 6x plus 9. So I'm going to get a x squared minus 6ax, and I'm going to get a plus 9. Got to do some algebra to understand that. Okay, now I'm going to multiply through here. You're going to get bx squared minus 3bx plus the cx. And all of this has to be equal to this numerator, which has not changed. Right, so I have two polynomials which are equal to each other. The only way two polynomials could be equal to each other is if all the x squared terms here on the right side equal the x squared terms here on the left side. So that will lead to some equations. Okay, that means that this 7 is got to be equal to, let's see over here, I got a, I've got b. When I add a and b together, which are squared terms, it's got to equal to this squared term. Let's see. I've got the x terms here. Let's see. The x terms on the right side are negative 6a. Let's see. I got a negative 3b. And I even have the c. All of those x terms have to equal this x term. So the coefficients of these x terms have to equal the coefficients of this x term. The coefficients, the sum of the coefficients of the square terms have to equal to this coefficient of the square terms. That's where I'm getting these equations. I'm looking at coefficients only. Okay, now let's look at the constant term. Here's the constant term, 9, just 9. Here's the constant term, 45. You know what? That was a 9a. Oops. That was a 9 times a. That's a 9a. Oop, my mistake. Missed an a there. Okay, so sorry, that's 9a is the constant term. And the constant term over here is 45. Almost made a fatal mistake. Okay, now that we have these three equations, you could arrange these in nice columns, make a matrix equation. You could use reduced row echelon form. Reduced row echelon form, yep. And you would have to use a very large matrix. You would have to use 4 columns and 3 rows. You have to use a 3x4 matrix when you build that. I'm going to do the easiest method. The easiest method is to solve it just the way it is. Like right here, I get one equation, one unknown. It's extremely easy to solve. I know here I'm going to divide both sides by 9, and I'm going to get a is equal to 5. A is equal to 5. Right? Because 5 times 9 is 45. Okay, now I just found out that a is 5. Now I think there's a 5 right here. A is 5. So I'm going to subtract 5 from both sides. So 7 minus 5 is 2. The b has got to be 2. Following along? Okay, now here's going to get a little bit interesting. And I'm going to do the side work up here since I've got some space. Okay, so I know it's negative 6a A is 5. Minus 3b, minus 3, well, b is 2. Plus c is equal to negative 35. Great. Let's solve it. What do I get? Negative 30 minus 6 plus c equals negative 35. Okay, so that's negative 36 plus c equals 35. Sorry, negative 35. If I add 36 to both sides, I get c is 1, which I'm going to write right here. c is equal to 1. Okay, there's all the work. I'm going to be deleting that right now. And there you go. So let's now put this back in as an equation. Let's get my colors right. Yeah, let's leave that green. Okay, so I know now that this is a over x. A is 5. I know that b is 2 all over x minus 3. And I know, let's see, c, yep, okay, that's all working out. So since c is, it is positive. No weird negatives. And I'm going to put that there, x minus 3, that quantity squared. And there's your answer. Okay, so your answer is this giant expression with the original problem, and it's the sum of these 3 rational expressions. There you go. Well, hopefully you've enjoyed this. Hopefully you'll go back to MathGuide, check out more videos, check out some interactive Quizmasters, and of course, hundreds and hundreds of lessons. Take care. Partial fractions? Why do they call it partial? They look like full fractions to me. Partial. Man, I'd hate to have to integrate that whole original problem. Boy, it'd sure be a lot easier to integrate those parts. Oh yeah, fractions broken up into parts. Oh yeah, now it's making sense.